Hi, this is a new series that I've decided to start recording with very little editing, if any, on various projects and obscure little technical things, in electronics specifically, that I've decided to record. And there's not really any rhyme or reason, but I've decided on the name FishingForTech after consulting the propaganda group, aka my friends, and I figured that we'd start off with Don Lancaster's binary to hex converter. This little number here is one of the most fascinating things that I ever came across when I was learning electronics first, because I learned it in reverse for some reason. In the late 2010s, I decided that, now's a good time to learn vacuum tubes. And I learned vacuum tubes, roughly, and then I figured out how to put together a color demultiplexing and whatever have you, all that silly analog stuff, and then I learned transistors, and I was getting into integrated circuits, moving chronologically because that makes the most sense, of course. And I came across Don Lancaster's TTL cookbook. Well, actually, in fact, I came across the CMOS cookbook, but that's this, but with some additional stuff. But this book, the TTL cookbook, has within it a delicious little tidbit of mind you, mine is worn for wear and came from an estate sale of. It was well used by an older gentleman, I'm sure, but if I can find it, and the page hasn't fallen out, I believe it's around here. It's always really easy to access because the page is nearly falling out. Yes. The thing described here is, well, one, he describes how to do a 4 to 16 line decoder for decoding binary into useful hexadecimal 7-segment display output via diodes, if you're into that sort of thing. And then he goes on to describe a method in which to decode into 7-segment characters. And he has this nice little pattern chart flowing along the right side here. The outputs in segments from A to H here, and the input. And the way he's done this is he has this first line over here being the address of the memory, the secondary line here being the output or the data payload on the ROM at that address, and this pattern here being what is displayed on the 7-segment display. In this way, you choose an address and it spits out a 7-segment code for that character. Very easy. Now this one is from 0 to F. But if you had more inputs, and I mean you have quite a bit on a ROM, you could theoretically decode any character sheet that you wanted. And it was very common to use these for characters back in the day. I mean, obviously they were used for many things, but characters was among one of the things they were used for. And I really thought that this was, this kind of changed my perspective on how integrated circuits could be used, because I was so into 74 series logic and 4000 series logic, and you can kind of easily fall into the trap of realizing you can do pretty much anything with that logic, and you get stuck in that mindset. And he's just like, well, you could make a big complicated logic array, or you could implement logic using ROMs. So I think it'd be fun if we went ahead and implemented his decoder in a ROM. And I have an appropriate EPROM here, UV flashable, the highest of tech. I don't know if we'll ever focus on that. Probably not. That's all right. But we are going to create his character sheeted decoder here. And that's about all we're going to do today. We'll show you what it looks like on the breadboard for each character. He does a couple letters different than we do nowadays, and it's kind of an artistic choice, I suppose. There is still an art to choosing how to display a character with such a small selection of segments available. And I'll probably go into making a custom ROM to do that with some interesting 9-segment displays in the future. But for now, we're going to go through and just implement this bit by bit in a ROM. And I will switch over to the computer and we'll do just that. Alright, so here we are in the XG-ECU Pro application, so it doesn't really matter what application you're using with your programmer as long as it's right for it. For this one, we're going to be using GC whatever Pro. It's the one for the TL866. And we're going to come over to here, ignoring all the rest of this, because this is not a tutorial on that. There's plenty of those tutorials out there. But we're going to go ahead and switch over to our NMC27C32, under all, preferably. And it's a Fairchild part, and here it is, the DIP32. No, it's not. Where is it? No, it's not. Where is it? There it is. It's a DIP24. Okay, so here we go. We have our full of FFs, because it's an EPROM ROM, and it's our standard blueprint for it. This is just a profile that's saved into the program. But what I like to do is I always like to hit read before I save the blank file that we'll be working with. Yep, and we've read the chip in the socket, and yes, it's all F's all the way down. Always has been, probably. So we have our file. We're going to go over to File, and we're going to go over to Save, and we'll do a save. And well, I mean, this is what we're going to do. We're going to save it under a folder called MD-ROMs under the name of our chip, and it's already in there, so I'm not gonna do it again. I will detag the @dip24 though, and we'll save it. And it tells us it's fantastic. We already know that. We're gonna minimize this, and we're gonna hop into Notepad++. And an important thing about Notepad++ for this, and really editing ROMs in general, is you're going to want to pick up the Hex Editor plugin. Again, there's tutorials on how to get the plugins. It's not a tutorial on that. And we're going to go ahead and hit View in Hex. Now, we have nothing in this because this is not the file, so we're going to go over to here, Open. And we have this empty ROMs folder. Either of these will do. They're both the same thing, different times. And what we have here is an empty ROM, but it's completely indiscernible in this specific output. So we're going to go over here to View to Hex, and if we scroll down, we see that every address line on this, byte per byte, is full of high state ones. So using this, we can edit this in binary. Oh, I should mention this. Let's go over to hex options, and this guy right here, hexadecimal binary switch, is the one that you're going to be looking for if you want to edit this in binary, that is, which is bit for bit what we're going to be doing here. I'm sure if you knew your ASCII codes and your true null zeros and all that, you could do it with your ASCII or hex editor, but I don't, and I prefer saying it in binary because we're bit banging here. So we have our addresses, we have our fields we can edit, and we'll do just that. Now, the blueprint that Don Lancaster has in this book that he's written is a fantastic layout, but something that I ran into when I originally did this is that the order that he has on the output is not a high bit low bit order. It's A through H from left to right. So we need to swap his code around. That is to say, if we are looking at 1 1 1, the rest are zeros to H, then it needs to be 0 0 0 0 0, and the last four, or rather last three, are ones. So we're going to do just that. We're going to bit flip, or rather sequential flip the data on each address. And I'm going to do that. You can basically get the idea. I'll do this one. So we're doing for 0, all of these are going to be ones except for G and H. Now, it's a high bit on the left and a low bit on the right of this data payload on this byte. So what we want to do is ensure that our G and H, which are our high bytes all the way on the left over here, are 0 and 0. We're going to bring our ones all the way down, and that's a 7-segment 0. On our 1, we have a low bit on the A, high bit on the B, high bit on the C, low bit on the D, the E, the F, the G, and the H. In other words, the only two segments that we want on are B and C. So I'll do all of these and I'll come back to it, and when I have it on the breadboard, it'll make a lot more sense what I'm talking about. So I said that I was done and I was going to switch over the bench, but I feel like I should clarify what I meant when I said that I was flipping these. What I really should have said was that I am mirroring these. Whereas his book lists the outputs necessary for the 7-segment from segment letters A to H, it doesn't represent the level that you would want if you wanted output line 1, or rather output line 0 on your ROM to represent the A on the 7-segment, and output line 8 on your ROM to represent H on the 7-segment. So you wouldn't get it. You'd get everything backwards, which is unfortunately what I did, not realizing what the codes were implying. So I just wanted to clarify that. So this is the finished code, though. There's not much here. It's literally just 16 lines. And I feel like we can drop you guys off at the bench now. And, well, you know, I'll flash this. Let's flash this. Let's flash this bad boy. So we have our finished ROM over here. We're going to go ahead and save it as. Custom ROMs, Don hex decode, we'll call it. As a bin is what I'd like to do. I don't know if it will let me do that. All files, yes. Dot bin. And there we go. Save. We'll go over to here. Let's take a look. We already got the device fine. It's all squared away. Open our ROM. Custom ROMs. Somewhere here. Ah, Don hex code.bin. And there it is. There's the hex for those playing along at home. That's about it. We'll flash this thing now. Where is that on this thing? Oh, there it is. And away we go. Perfect. I will pop this out of here, pop it in the breadboard, and we can take a look at what this thing looks like on a 7-segment display. Alright, so we have our 7-segment display wired up to our ROM, with A being the output of 0 on the ROM. So output line 0 on the ROM goes to A. Output line 8 on the ROM goes to H. In that way, sequentially. So everything's wired up, and right now all of our address lines are grounded. Well, they're at 0 volts. So because they're all low, we have 0 on the output. So let's go ahead and manually clock, because I mean I could throw together something that automatically clocks, but I think it's good to take a look at what happens when we're moving around the address lines like this. We tend to look at address lines as something that's just handled by a microcontroller or a CPU, but really they are things that we directly manipulate, whether we know it or not. So let's move this bad boy, which is, looks like it's this one here. So that would be the 4th bit of the address line. Move that high. Well, what do you know? We have a 1. Let's check. Let's check what that looks like in the TTL cookbook. Here on Don Lancaster's chart. Handy that these pages are literally falling out. So if we look on the chart, we see that at address line 0 on our ROM, we have a 1. Everything else is grounded, so 0. That's all the way, too. And we have 2 bits that are high, and another bit all the way over here at the highest point that's high. Now, this has no definition. I'm not sure what he was doing with this, other than to maybe make this an active low trigger to count how many times the segment had gone to 16. I'm not 100% certain. He doesn't describe it anywhere, so that's fine. I just did exactly what he did and left this H line in this pattern with only 0 having a low bit on H and the rest of them illuminating the dot. So we can see here that the H is high, so we have on our 7-segment display, yes, the H is high because I have that wired into the dot. And if we look at the other two, B and C are also high. Well, what do you know? They are also high. So at address line 1, we're getting exactly what we wanted. And, you know, I could go through all of the digits, but there exist BCD to hexadecimal converters that will do numerals from 0 to 9. What there isn't is, and granted those are 4000 series and all that, what there isn't is a commercially available, or at the time when he wrote this at least, a commercially available hexadecimal converter. So let's go ahead and let's move into the world of the alphabet. Let's embrace the power of the alphabet, and we're going to do that by moving over our 4th bit, which is one of these down here. It'd be this blue one here, and this represents the 8 on the address line. We're going to move that high. We get a 9, and now we can start moving in and out address line digits higher or lower, or rather higher above 9 to get our alpha characters. So let's do that. This would be D. Now that D is pretty much what you expect, which means that we are at bit number 14. And that's fine. So let's go and let's put them all high. We get the F. Again, these are, you know, pretty standard character designs. D and F are pretty much always done like this. What I'd like to see, though, is the A. So let's see, I don't quite remember where everything is. Ah, there we go, though. Here's the A. The A is a little interesting. Now, normally what they do is they turn off this bottom segment. They turn on this segment over here, and you get a capital A. That's not what Don did. Don went for a lowercase a. Well, what does our B look like then? To get B, we need to pull U low and U high, I believe. So a little bit, everything's always a little bit iffy with the breadboards. That's a 9. That's not what I thought it was. One moment, please. And let me actually look at this thing here. There's our outputs. That's all fine and dandy. Here are, so this is 8. This is 4. This is 2, and this is 1. So let's bring 1 and 8 up. Well, that shouldn't be. Interesting. Is that the wrong? Let's do this. Ah, there we go. So here's C. C is a little bit interesting. It's kind of hard to do a C on a 7-segment display. There's not really a lot you can do. You know, you get a little bit of a small C. That's about it. It's just tiny C. You could go big, you know, I guess, which I think is the normal way to do it. But Don went lowercase here. Not really sure about the C. C's kind of weird. you know? Maybe I should turn the lights off. Well, I'll need to see the lines, but yeah, the C's kind of weird. Interesting. We're gonna go higher though. We want to see the D, or rather the B. We saw the D. So we need to go to 14. And here we go. Here's the D. I think we've actually seen them all now, unless did we not see the B? It's all kind of a jank fest. I probably should have actually done a sequential counter just for sanity's sake. See if I can get the B to come up. Not sure which one is which, and I keep forgetting which one is which. Probably would have been better if I bundled the bottom 4 address lines together rather than just willy-nilly bundling things, but you can basically see what I'm getting at. Let's do the 2. So this is the 2. So this is A. That's so weird. Why do we have a 0 there? I feel like our B has turned into a 0 somehow. You hate to see it happen, but, you know, these things do happen. Not really. I'm not sure why that's happening. Something's gone a little bit stank, but you get the basic idea. I think I've mixed up my wires. Regardless, this is the magic of the ROM here, and although it's a little bit awkward and confusing on the breadboard, it made quite a big difference back in the day when you could just program logic into an array like this and address everything in a manner like that. I suppose that's all I have to say on it. Probably should have planned this out a little bit better, but that would break the spirit of this series, so I won't do that. I will try and post every week a new video like this. Don't get your expectations too high on the quality, but it should be at least a little interesting. This has gone on long enough, though.